All right, off we go. So today is going to be another lecture about graphs, which is fun. And we'll focus on a problem called independent set. So, right, so what is independent set? Well, okay, here's some context. We've been looking at problems that aren't actually as easy as the ones we were doing before the first midterm, starting with this Boolean satisfiability problem. And by now we've started to build a number of connections. For example, 3 set turned out to be hard, 2 set turned out to be easy, max 2 set turned out to be hard. Subset sum, which looks nothing like sat, but turns out could solve sat. And then last time, looking for the longest path in a graph also turns out can solve sat, even though you can do shortest path in a graph. That said, if the graph is a DAG, you can solve this problem and many more. That's what we did last time. But somehow, the conversation has become a little bit more subtle compared to midterm 1 because not all problems are automatically solvable. So we already developed some reasonable set of tools before midterm 1, and now we're in this second world where we're just given problems, natural problems of interest, and we don't even know which one it'll turn out to be. Okay, so that's like some level 2 stuff. Okay, so today's problem is called independent set. So your input today, everything today will be an undirected graph. Okay. And so I give you an undirected graph, and the goal is to choose a lot of vertices that don't touch each other. So a set of vertices is independent if no two vertices are connected by an edge. So in this example up here, I've highlighted, I think, 5 of the vertices, and there shouldn't be any edge between any purple pair of vertices. Okay. So the independent set problem, the independent set problem is to try to find the maximum weight independent set in the graph if I put weights on the vertices. In a simpler case, there's no weights. Everything just counts as 1. You just want to choose as many as possible. Okay. You can turn this into a yes/no question by also giving some parameter k and saying, oh, is there an independent set with at least k vertices? So besides this in a general graph, we're going to look at 2 special cases. So the first special case is intervals. So this is a little bit abstract maybe, but I'm going to give you a bunch of intervals on the line. So there's some left endpoint and some right endpoint. Okay. And I'll say 2 intervals are independent if they're disjoint. They don't overlap with each other. Okay. You could think of this as a graph problem. If you think of each interval, as a vertex, so here I'm kind of drawing dots in between each one, and you have an edge between any 2 overlapping intervals. Okay, so they represent the conflicts. Something like this. So if I thought of the intervals as vertices and edges based on overlapping, then an independent set in the graphical sense will correspond to, that's what gives it the name, even if it doesn't look like a graph. So this is sort of like a special case of a graph. It's a graph induced by intervals, and there's certain limitations to combinations you can make with an interval. And in the other special case we'll look at is in a tree. Okay, so an undirected tree. So you just promise there's no cycles. Okay, so those are what we'll look at in general graph, in sort of graphs induced by intervals, and in trees. Okay, and yeah, our interactive part of the day, I've set up as usual a poll. Okay, so we're going to look at independent set in these 3 settings: general undirected graphs, intervals, and trees. And for each, we'll try to figure out if it's able to solve SAT, or if we can come up with an algorithm ourselves. All right, so who's not voting? All right, let's start with graphs. Who think it's going to turn out to be hard? Oh, lots of people. Okay. And then who thinks we can call it with an algorithm? Not bad. Okay. All right. Now, what about intervals? Who thinks that this will turn out to be hard? Okay. And who thinks we can get an algorithm? That's slightly more than last time. Okay. And then what about trees? So who thinks that the problem will be hard on trees? And who thinks we can get an algorithm? Okay. Uh, good. Good. So, uh, okay, this is at least makes some intuitive sense. These two problems are special cases of this one. So there's no way, I mean, there's no way that this has an algorithm and these don't. Although feel like at least one person voted that way. And yeah, okay, so that's the general idea. You know, if you impose some structure, then there is some chance that you'll do better here than in the general case. Okay. And if that turns out to be the case, it also becomes a comment about the structure of the underlying object. Oh, there's something simpler about it if you can do this problem on it. Okay, so we'll start with the general setting. And so the 80 whatever percent of you are right. We are going to show that if you have a black box for solving independent set, even in the unweighted case, you'll be able to solve 3-SAT. Okay. So we're going to start with a 3-SAT instance, try to come up with some kind of undirected graph, so that if I give it a black box to the black box, and then I maybe say, oh, is there or is there not an independent set of some size k? We'll have to figure that as well. We want to interpret that uh, to ultimately be a yes/no for this. Okay. All right, so that's the situation. Any questions about the setup? Okay. Good, good. Okay, so what do we want to do at a high level? So somehow I want to transform a 3-SAT instance into a graph so that, you know, something's satisfiable if and only if there's some independent set of size k or something. Okay, so I've left this part blank because this is the fun part to think about. Any ideas for somehow trying to convert a 3-SAT formula into an independent set of size k? Or, you know, inspirations. Okay, so maybe a reasonable candidate for k. I'll use m for the number of clauses. Okay. So somehow you should be able to take one variable per clause or something like this. Yeah. That's also possible. Can we instead do max reset or something? Uh, sure. I don't know if it'll be easier. I think the main conceptual point is how am I going to take a formula and turn it into something to do with graph. So that'll definitely be similar to I think what we have coming up. It's set up this way, but I think it'll be easy to see how to make it your version. But maybe the real thing is, how can I somehow, or somehow being able to choose a vertex should kind of look like satisfying a clause or something. Yeah. Okay. So if I had a clause like x1 or x2 or not x3, you're saying I should make three literals, like vertices corresponding to the literals. So you have three vertices like this, x1, x2, x3 bar. And if we connect them with edges, uh, something like this, it's like, okay, you can get at most 1 point from this clause if you can choose one of these literals or something, right? That'll be one clause. So if I had another clause, like x2 bar, or x3, or x4 or something, uh, so I guess I would make another one, x2 bar, x3, x4. Okay. So your goal is to try to choose. So every time I make one of these triangles, I can only choose one of these vertices in an independent set. So you can only get at most 1 point per clause. So that maybe is a good start, like at least for pattern matching. Now, I shouldn't be able to take x2 and x2 bar, right? Okay, so we can connect them. So if I connect them, and I connect x3 and x3 bar, now this is saying something like, okay, you want to try to take one from each triangle, but you can't take things that are like conflicting. You can't take x2 and x2 bar. Now they're connected by an edge, x3, x3 bar. Yeah, so that's I think what we're gonna do. So literals are gonna map to vertices. Clauses will map to triangles. Um, so this one will give you a triangle like this. Okay. The triangle enforces that you can only get 1 point per clause, one vertex per clause. If I had another uh, clause like this, the triangle would look like this. And now to encode the conflict, I put an edge between A and A bar because I can't set them to be true and false. Okay. A more involved one might look like this. So here's maybe four clauses. So that's going to generate four triangles, like that one. Oops. Oh, it's gonna be a little complicated. Or that one, or okay, something like this, right? So there's four triangles. Someday I'll learn how to properly animate things, right? So this is one triangle for each of the clauses, okay? And now we just have to draw all of the opposing edges. So I guess there's like one like this, one like that. You could tell me if I miss one. I always do. Something like that, something like that, 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 that. Oh, I just did that twice? Okay. Am I missing any? I have no idea. Okay. I drew this in advance, but I also don't know if that's correct. Okay, but you get the idea, right? Um, okay. So I guess I said this one so we can go a little bit more slowly. I often go a little faster this part. So what we want to say is that given that formula F with M clauses, I want to argue that F is satisfiable if and only if there's an independent set of size M, right? This way, the yes for the original problem corresponds to the yes for our new problem, and vice versa, right? Yes means to mean yes, and no means to mean no. So we have to just double check these things. You're gonna have to do two arguments. So we'll do the opposite argument next, right? And I was commenting to someone the other day. Often, if you have a good, clean construction and you can see it clearly, often this proof is not so hard. You're just going to write out the part you already understand. If you don't have the right answer, then you're going to probably find this part to be very difficult, right? Because proofs are going to be self-evident and stuff like that. So if you're saying, "Oh, why do I have to do this? This is so boring," that's a good sign, right? And then, because sometimes when I see when that's not correct, I say, "Oh, I wish they had tried to double check and write out the proof. They would have noticed what was missing or something," right? So, proofs are ultimately just to verify something that's actually correct, like a mathematical proof. It's not like an opinion, right? It's like really a logically true thing. So these are all uh, tautological things, right? Our opinion doesn't really matter, so it's just giving a certificate. Okay, so let's go through this slowly. Suppose F is satisfiable. I want to argue uh, that there's an independent set of size M. So how would you write it out? Yeah. Okay, so but let's just take a step back and walk through it a little more mechanically, right? So I think you're just skipping a little bit of context, right? So you might want to start with a sentence like let x1 to xn be a satisfying assignment, right? I think you should be like, oh, okay, let me just take the input and literally map it over to the input of the other problem. So we just do it a little more mechanically so that someone who I mean, what you said makes sense in the context of our conversation, but imagine someone else is reading from the outside. So let x1 to xn be a satisfying assignment, right? And now, you want to show that there is a independent set of size m. So let's just make one, right? Let's just try to figure out how to choose m vertices that are independent. Okay, so if you have this, what might be the second sentence? Yeah, that's exactly what we're gonna do. Yeah. Oh, okay. Okay, then say, so I think it's understood what the graph is. Now we just have to take our assignment and turn it into an independent set. So we just want to choose the vertices. So I think implicit in the lemma is it's referring to an independent set in something. So I think that context is established. But now we just need to pick out the m vertices and double check it's independent, and we're done. So what might be just one way to put that in words? Yeah, yeah. So, but which vertices are we going to pick? That's all I'm asking for. Those are variables. Okay, so let me give you an example. So we can say something like for each clause, choose a vertex uh, from its gadget corresponding to a literal. It's a little bit my wording's not perfect, but in the assignment satisfying a clause. Okay, that's a little wordy, but I want to make one distinction, or one particular distinction. In our construction, a particular literal like xi or xi bar actually appears many times, once for every clause, right? And some of the things that I think we're all on the same page, but the things that were being said out loud weren't necessarily making this distinction, right? So let's just make it really explicit which vertices we're going to pick out. Even this wording is a little bit high level, but it's at least more precise on that point. You know, each of these clauses, we have some triangular gadget, and one of these corresponds to some, you know, something, the reason why the clause is satisfied, right? We'll pick that vertex in particular. So just saying, oh, we'll pick xi bar is still a little bit ambiguous because xi and xi bar appears in multiple places. Even this probably could have been written a little better, but you know, I'm on the spot and stuff. I'm sure I could type something better. And now we just have to double check that it's independent. So there's you just say like, okay, this gives m vertices. You know, one from each clause, right? Because we wanted to check that we're picking m of them. You know, and it's independent because, you know, of two things. We only have two kinds of edges. One is in between the clauses, right? So it's one vertex per clause. And then the other kind of edge is choose the opposite literals. Something like, okay, only one literal possible, which is from the assignment, per variable. Okay, my handwriting is just degenerating, but that's the idea, right? Okay, you start with a satisfying assignment. Let's make explicitly the m vertices, verify there's m of them, verify there's no edges between them, and then we're done. Okay, it's a little bit boring. This is more useful for the problems you didn't solve correctly. Yeah. Yeah, we could have a clause all by itself or something. You mean no purple lines? Yeah, that's entirely possible. But ultimately, I guess to show that it's independent, I know from my construction there's only two kinds of edges. So the edges are the constraints. They're the bad things. They're the conflicts. One type of edges is from the things within the clauses. And there, in the most childish handwriting, I wrote, you know, I'm only choosing one vertex from each clause, so that's okay. The other kind of conflict is coming from opposite literals. Again, in the handwriting of a 5-year-old, I meant to write something like, well, I can only choose one literal from each variable because that's the literal corresponding to the assignment. So I just double checked that, oh, we don't violate any of those types of edges, so it's independent. And good, that's one direction. So you just take this and you dump it into ChatGPT and it'll make it like sound more intelligent. But there is like informational, you know, important just things to make explicit. Okay, so don't go too rapidly through here. Yeah. If it's too boring, great. Great. Okay. It should be boring if you have the right answer. Just checking things off and at some level explaining your construction. Okay. That case should be M. So what we just showed is yes means yes. So if F is satisfiable, well, depends on which yes comes first. But we showed that if the F is satisfiable, then there is an independent set of size M, right? Now we're going to kind of do yes in the opposite direction. If there's an independent set of size M, then the F is satisfiable, which is the same as saying if F is not satisfiable, then there is no independent set of size M. The fancy word is contrapositive, I think, anyway. Okay. All right, so let's do this also relatively routine thing, right? Let's say you have an independent set of size M. So, okay, so let's, let S be independent set of size M. Okay, so now we need to construct a satisfying assignment. How do we describe that? So you have this independent set of size M, and you just want to read off a satisfying assignment. Yeah. Okay, for each xi, okay, so maybe you might something right like I'll set xi to be true if some xi vertex is in S, and then if some, I don't know, this isn't probably a perfect explanation either. That's okay. And maybe it's worth pointing out first, uh, S can have, xi vertices or the not xi vertices, but not both, because it's independent, right? Because otherwise, if you wrote this as code and both of these came out to be true, okay, your computer would crash and burn. Um, or ChatGPT will get an infinite loop or something, right? And so, I mean, you all know this, the logic. But we're just bringing it to surface and making it explicit, right? So yeah, that's also possible. Okay, so what should I do if xi or not xi, neither of them are in S? I mean, some vertex labeled xi or xi bar. It wouldn't matter. Hmm? Yeah. So you can write either or true or false or whatever, either, or you can just set it to be true otherwise. Okay. So good. We've at least have a well-defined assignment. And now all we have to check is that each clause is satisfied, right? So you want to say that something like, x1, or you can say something like, okay, for each clause, you know, C, C is satisfied because, uh, yeah, to pick one vertex from C's gadget to have uh, independent set of size M, and that vertex variable will satisfy C or something. Something like this. Okay. Again, this can also probably be done more elegantly and certainly more legibly. So, but it's the high level points I want to hit, right? Okay, you start with some independent set of size M. You explicitly construct an assignment, address some of these ambiguities. What if neither one appears? Point out that you can only have one or the other so that this is kind of well defined. There's no conflicts. And the next thing you need to do is say, oh, let me convince you that this is a satisfying assignment. Well, the only way to get M, given our construction, is to choose one from each triangle because there's M triangles and you can only choose one from each triangle. And then that'll give you that literal with the variable that'll satisfy it. Okay. So usually by the time you've done like all of this clever thinking, most of this is probably in your head. There's nothing too surprising. Just get it down on paper and explicit. And then you'll be convinced that your own reduction works. Okay. So you don't have to be too clever here. Just be straightforward, clear, explicit. Yeah. Okay. Okay, good. That was fun. So that is our theorem. Yeah, so the trick is to do this triangle with extra conflicts. So somehow, yeah, you can encode, yeah. So anyway, somehow independent set, which would have seemed to have been a simple problem, at least it's simple to define, again, can capture any Boolean formula, right? Which is sort of surprising. Okay. Yeah, maybe this is simple in hindsight, but it's not so simple or obvious going forward. Okay. Any questions? Okay. So that turned out to be hard. Let's move on to intervals, which I believe most people thought was going to be easy. Okay. So if you thought it was going to be easy, then, and I guess I'll do weighted just for fun, because last time we didn't do weighted. What are some ideas for an algorithm? All right, let's at least start. Okay, work with me then. Let's start with a recursive algorithm, right? So who wants to define like some sentence capturing our problem that can be extended to subproblems? I'll start. I'll write MWIS for maximum weight independent set. So I do the biggest intervals first, like this one. Okay, so uh, okay, so something like, and I guess there's weights too. So given n intervals in decreasing order of length, um, the maximum weight independent set of, these intervals or something, right? Okay, so if I wanted to implement this, you can do that too, including I1. Yeah, so I'm assuming that these are already ordered in decreasing order of length. So I1 is the first one, so including I1, that's what you have in mind? Okay. Okay, so if I wanted to implement this, maximum weight independent set of I1 through IN, I should probably have the weights in there, but that's okay. What would I do? What would be a base case? Okay. N equals 1 implies I'll return the weight of I1. I'll write W of I1 or something. Okay. What if N is bigger than 1? Okay. So I look at, oh no. Okay. So I'm looking at the biggest interval and you're saying, okay, I have to include it. So it'll be WI1 plus, and then I look at all the next biggest ones. Next biggest overlapping. So IK, IN, where K is first interval not overlapping. Okay. Now I have a question. So let's say I take this interval, right? And then this would be IK. This will be the next biggest interval. And the next subproblem you say, okay, I'm going to take this. Now, once you've taken this, your algorithm is going to forget that it already took this. So maybe the next choice will be like this one. And it'll be tempted to take this one because it forgot that it already took this one. Okay, so you want to throw away everything that overlaps with this? Okay, so I think that might look a little bit more ultimately like this algorithm. Okay. You could order it, or you could imagine here I always pick the biggest interval. But this is sort of a recursive algorithm that's taking a family of intervals of some kind and trying to get the maximum independent set. If there's no intervals in your family, you return 0, nothing you can do. Otherwise, we'll choose some interval. For you, that would be the longest interval. And I can either not use it, or I can take it and throw out all the intervals disjoint from it. Okay. But here, I will throw out all the overlapping intervals. Okay, good. So what's the running time of this algorithm? Yeah, so this might only throw out one interval or something, right? So you have one of two choices, and then you have two subproblems. So ultimately, you sort of have a subproblem for every possible subfamily. Um, and okay, so the question is, it is correct though. This will return a maximum weight independent set. It's just too slow. So the only question is, how can I make this fast? Yeah, I'll give you the values of the intervals. Yeah, so I'll just give you the values of the intervals and the weight. And then if you want to find the first point, you can just look at all the AIs and find the smallest one. Okay, so that's what we're going to do. Well, I did the left endpoint. We'll see if the distinction is important. Okay, but letting AI denote the left endpoint, BI denote the right endpoint. I'm going to sort an increasing order of left endpoint. Okay, so here you can see the things are numbered, and then I'll just assume the indices are already ordered. So this is the smallest A1, second smallest A1, AI, so forth. Okay, so now um, we can write out this thing. Let's get the maximum weight of any independent set of IK through IN, ordered by left endpoint, right? So at some level, we already have this intuition. There are some exceptions like subset sum, but one thing great about longest increasing subsequence is that it's a sequence problem, right? And you just look at subsequences. So at the very least, we've turned this into a clear sequence problem. Okay, is it going to be strong enough? Let's find out. Um, okay, so what would be a base case? Yeah, so k equals n, then I'll just return the weight of ik. Also, k bigger than n, I'll return 0. Okay, so now what are we going to do in the general case? Okay, so we'll return the maximum of, if I don't take it, then that will be k plus 1. And if I do take it, I'll get the weight of the interval plus, yeah. Okay, good. So if I take interval 1, if I take this interval, then I know that this interval is I can't use anymore. I know that interval I can't use anymore. And now you can see why it's convenient to order by the left endpoint, because all the intervals that are going to conflict with me, they're going to be a beginning of the list. Because it's only if the left endpoint is overlapping my right endpoint that it conflicts. So left endpoint turns out to be convenient, at least if you're going from left to right, for turning this into the appropriate sequences. WIL, or sorry, L, where L is sort of the min, such that IL and IK don't overlap, so right, the intersection is empty, or otherwise, I don't know, L is equal to n plus 1 or something, and then you'll get 0. Okay, so you take it or you don't, but the great thing is that ordering by left endpoint, you get nice subproblems. Okay, so that would be the algorithm. And so what's the running time with caching? I use dynamic programming. Yeah. Okay, so there's n problems. So first we have to sort. So there's some n log n pre-processing. Don't forget that. Sometimes some pre-processing does matter. So there's n problems, and how long does it take for each subproblem? So at least naively, it's going to take on because you have to search to find the interval. It should be what? Well, so I'm going to be comparing my right endpoint to the rest. So it's not that obvious because, let's see if I can find an example. Uh, yeah, so if I'm looking at this problem, right, I'll go from the right endpoint and search there. But here's the next interval with the endpoints even smaller. So it will rescan some of the same intervals. So it's not completely disjoint if I understood your point correctly. Okay. All right, so that's n squared time, but does anyone see how to make this thing faster? Yeah. Yeah. Ah, okay, I can binary search for L. Okay. So if we play the over-under game, we can find the first L and log n time. And is it written? Yeah. So you'll get n subproblems and log n time per subproblem, so you get n log n overall, plus the n log n pre-processing to even sort the intervals. Okay, so you can get it down to n log n. Okay, let me try to speed run through the last version, which is in trees. So we don't have to talk about independent set next time. Okay, so, all right, any ideas for how to make an algorithm? There's going to be an algorithm. Yeah. Okay, I can pick a leaf node and start. So if I pick it or I don't. Now, I guess one thing is if I want to use something like dynamic programming, it'd be nice to come up with some kind of order or, inductive structure so that I could say, oh, there's only a small number of subproblems. So how do I how can I bring some kind of sequential or hierarchical order to a tree, something that I can apply induction to? Sorry? Not quite topological sorting. It's not even a directed graph. Okay, so I think maybe what you have in mind is sort of similar. So what we can do, well, okay, there's no time to do the full thing. I can fix a root. So I'm going to say, oh, I'll pick this node, and I'm going to call this the top of the tree. And I'll kind of draw it like this. So if I had more time, I would have done the cut and paste where I kind of grabbed this and dragged it down, grabbed this, dragged it down, grabbed it, dragged it down, and fixed up those edges, right? Because now I can talk about subtrees and subtrees of subtrees and subtrees of subtrees. That gets smaller and smaller and smaller. In the smallest case, you have a leaf, right? So I can actually solve a subtree and then, use those subproblems, right? So the real thing is that the subtrees will give you some structure to do some induction. So, all right, not much time, but you can do something like the maximum weight independent set at the tree rooted at V. Okay. Now, if you try to implement this, what you're going to find is something like this, right? So here's our tree. And then you're going to say something like, okay, suppose I want to put this vertex in my independent set. Then down here, I want to get, for my subproblem, a big independent set, except it's not allowed to have the root. Okay? So I want to make my subproblem stronger. So if I guess, oh, I'm going to try putting the root in my independent set, I could tell my subproblem, you're not allowed to use your root because that'll conflict with my choice. If I don't use this, then I can just get the maximum weight independent set. So normally this is a good teaching lesson, but today we have 50 minutes. So you'll need to strengthen your recursive spec with an extra flag that says, oh, you're allowed to use the root or not. Okay? Otherwise, you're going to do what you kind of expect. If you're not allowed to use the root for your subproblem, then all your children are allowed to use the root. So I'll just get the best independent set for each subtree and add them up. Or um, or either I'm not going to use a root and I can use MWI as true, or I can take my node and tell all my children that you can't use the root. Okay. So that's the idea. I'll make this quick. The running time is, you want to sum up the time you spend at each vertex over the two subproblems, and roughly how long would that take? Huh? Because, yeah, so these loops are really proportional to the number of children of that particular vertex V. And then you're just counting all the vertex, children once, so it all adds up to O(n). So in a tree, M is n, but you end up with an O(n) time algorithm. Okay. So that was a little bit quick, so I'll make sure to give some homework to let you process this more slowly. But the point is that on trees, you can often do some induction dynamic programming because the subproblems come from the subtrees. In general, you're given a structure, try adding the prefix sub and seeing if it's useful is a reasonable strategy to solving problems. Okay? All right, thank you.